But that's not quite, that's harder than
That's other than two, but it doesn't make it like it's right? Again, one part of SL2C is just multiplying everything by number.
so it's specific complex linear combination.
Yeah, you
Still,
do
that's
this
what's
stuff.
supposed to be.
Welcome. We're going to begin. Do we have any visitors today?
I'm back on the goalies, same as last week.
Great. Okay.
Colombia on sabbatical.
I'm Alessandro Podo. I'm a postdoc at Columbia and work with Alberto on this thing.
Excellent. Excellent. Today we have Oren, Slone, a postdoc here, who's going to tell us about the dark sector and astronomical probes of it.
Okay, yeah, approximately. So, good. Okay, so yeah, so basically what I'm going to be talking about today is dark sectors that are dark matter that is completely secluded from the standard model up to gravity. Okay, so I'm going to tell you how you can take these kinds of models, and if they fall into specific categories, you can try to probe them using astrophysics. Okay, along the way, I'm going to talk about kinetic theory and basically how you can take a bunch of particles and model them as a gas or as a fluid that have like macroscopic properties such as temperature, density, that kind of thing. And then I'm going to talk about astrophysical probes. So I'll give you a few examples, and most of this talk I'm going to be thinking about specific models of self-interacting dark matter, but a lot of what I'm going to say can be generalized into more complicated things. Okay, the outline, for whoever can see it, is I'm going to start with a little bit of like the philosophy of how this can be done. I'll give a few examples, and then I'll like write down a specific model that will be like the model that I'll talk about for this talk, but again, you can generalize it to other things. And then for that specific model, I'll tell you what the current status is, what bounds and signals exist for that kind of class of models. And then I'll talk more generally about specific self-interacting dark matter, so SIDM, self-interacting dark matter, and what the dynamics of these models really is. And it's different from what like people have been studying typically for the last 10 years, because it turns out that dynamics is important. So these things are out of equilibrium, and that out of equilibrium behavior turns out to be super important. And then I'll talk about how to like form what the formalism is in kinetic theory and discuss the probes. Okay, so let's start with the philosophy. And so the general idea is you have some Lagrangian or you have some particle physics model, whatever it is, and you look at that model and you ask what are the important diagrams in this model, and you ask the question, can I map the micro physics of that diagram or those diagrams into some macro physics? Okay, so what do I mean by that? For example, let's say you have a model that looks like this, and you have this diagram. Okay, so a diagram that gives efficient self-interactions in the dark sector. So imagine that these are your dark matter particles. There's some mediator, doesn't matter, some self-coupling. So if this is an important diagram for astrophysical purposes, then you might be able to map this onto efficient heat flow, in like a fluid description. So imagine you have, some dark halo of your self-interacting dark matter. This diagram is important. Maybe heat can flow efficiently from the outskirts inwards, or maybe in the opposite direction. And this would be like a macroscopic kind of thing that you might be able to search for. And I'll tell you how to search for this in a second. Another example, let's say you have, a very light mediator and the coupling is large enough so that you can radiate away the light particle. So that might correspond to global dissipation, right? So loss of energy from your dark halo. And so if you can do a mapping like this, and in your, macroscopic description, these things also change the gravitational potential somehow, then you can search for that effect in gravity. Okay, so that's the general philosophy. Take the important diagram in the dark sector, you map it onto some macro physics, you try and get a fluid description of that macro physics, and you ask the question, does that macro physics have a gravitational signal? And then you search for it in astrophysics. Okay, so that's the general picture. Okay, so now let's move on. So let's take a specific model. Okay, so an example model. And the model I want to think about today is just it's just the top diagram here. So I want three free parameters in my model. Those free parameters are going to be a dark matter particle m chi with some mass, a mediator m phi, which is going to have some mass which is lighter than m chi, and some self-coupling dark sector alpha d. Okay, and so let's just be very concrete. Let's consider the model where the dark matter is a fermion and where the mediator is either a scalar or a vector. And so the self-coupling is either like a dark fine structure constant or some Yukawa coupling squared. And this is the only diagram that I care about. Okay, maybe you also care about the U channel. So let's just be concrete. Let's say this is the diagram I care about. Okay. This is the model I'm going to be considering. And so if velocities are much smaller than 1, right? If we're highly non-relativistic, then you can work in the language of potentials. And in the language of potentials, the potential that you care about is going to be alpha d over r times e to the minus m phi r, right? Some Yukawa potential. Okay, so you have a Coulomb potential with some cutoff, where the typical range of that cutoff is 1 over the mass of the mediator. Good. And so if you now work in the Born approximation, okay, so small enough couplings such that bound states are not important, and the Born approximation is a good approximation, and you plot cross-section per unit mass as a function of the relative velocity of the incoming particles that are being scattered, what you find is that the cross-section looks like this. You get a cross-section that's constant and then falls off. Okay, this is a log-log plot. And so what's going on here? What's happening is as follows. If you're at very low velocities, much smaller than the typical scales of the problem, and I'll tell you what that scale is in a second, but if you're at very low velocities, you don't have enough momentum transfer in the propagator to get through the Yukawa barrier, and you just see point scattering. Okay? So at very low velocities, the cross-section goes like alpha d squared times m chi over m phi to the 4th. And maybe there's a 4 pi. Okay, I'm going to just give this thing a name. I'm going to call it sigma naught over m chi. Okay?
What if it is attraction?
Yeah, I mean, if it's an attraction, then, well, the cross-section is the same, but the dynamics might be different, right? I mean, you're asking the question, if when the two particles get close to each other, do you do this or do you do that, right?
But you justified constant cross-section just by geometrical things. So if I have 2 billion balls, there will be a cross-section which doesn't depend on velocity, correct?
Right.
Is it the right thinking, billion balls?
You're asking for the case of an attractive potential is the right thinking of billiard balls.
But am I thinking right? This cross-section is constant just because it is a geometrical cross-section? Then it will only work for repulsive potential, right?
Yeah, but it's not that it's a geometric cross-section, it's that the momentum transfer is much less than m. I mean, I need to think about if you can think about this as a geometric cross-section.
Am I quantum or classical? Yeah, whatever. Maybe it's irrelevant.
Yeah.
I don't know.
You're quantum, right? I don't think.
If I'm quantum, then the sign probably wouldn't matter.
Yeah, so I think you're quantum and not classical.
Okay,
If
great.
you're classical, the cross-section actually does not go to a constant.
So I shouldn't think billion balls.
No, I think you shouldn't.
Okay, great.
Yeah.
This is just this Born approximation.
Exactly.
Okay, great.
Yeah. Exactly. Okay. And so if you go to a large enough velocity such that m chi times v is approximately equal to m phi, so a velocity that's equal to m phi over m chi, which I'm just going to call omega. Okay, so in natural units, this has units of velocity. If you get to this velocity or above, you just see, you just see the Coulomb potential, you just see alpha over r, and then what you get is Rutherford scattering. Okay, so Rutherford scattering goes like v to the minus 4. I'm going to leave this like as a pre-parameter because you might have identical particles, in which case the U channel is important, and then it's not exactly Rutherford, it's more molar scattering. But no matter what, given a Lagrangian, you know what this n is. And you can calculate it. Okay, and so even though this model has, 3 free parameters, m chi, m phi, and alpha, the truth is that in astrophysics, all you're ever going to be sensitive to is 2 combinations of those 3 free parameters. And those 2 combinations of this and this. And so everything I'm going to tell you for the rest of this talk is going to be in the language of these 2, parameters that can be searched for in astrophysics. If you want to get another constraint and actually, say something about the underlying parameters of the theory, you need a third equation or a third kind of constraint, which can come from cosmology, but I can talk about that at the end of the talk if anyone's interested. Good. Okay. So what I want to do now is, I'm covering the top on purpose. What I want to do now is I want to put some scales onto this thing, okay? And I'm going to tell you what the kind of current state of affairs is, okay? So current, bounds, and signals, okay? So not everything I'm going to tell you now is bounds. There's like kind of some evidence in the data for these types of models. And so let me just make this plot again. Okay, so the x-axis here is VREL, and the y-axis here is sigma naught, is sigma over m chi. Good, and let's put some units onto this plot. So I'm going to think about 3 different types of astrophysical objects. I'm going to think about dwarfs that probe like 10 kilometers per second, approximately. I'm going to think about Milky Way-like galaxies, which probe like 100 kilometers per second, and I'm going to be thinking about clusters that probe like 1,000 kilometers per second. Okay, so these are dwarfs, galaxies, and clusters. And the numbers that I'm going to care about here are like something between 1, and this is going to be in units of centimeters squared per gram, 1, 10, and 100. Okay, so most famously, there is this bound from this thing called the bullet cluster, okay?
What if m phi is greater than m chi?
If m phi is greater than m chi, then you just get, I think, just constant cross-section, right? You'll never be in this regime, so you just get a constant cross-section. I mean, everything holds. Oh, you're saying that then this number is large?
This number makes no
Yeah,
sense. but
this
whatever,
number makes
you are
no
saying
sense,
it
but
will
you'll
just
still get a
constant cross-section.
Yeah,
That's
yeah,
it.
yeah.
Okay.
Yeah, exactly. Heavy mediator, right?
Okay,
Super
great.
heavy mediator. Yeah. Yeah, you just integrate it out, right? Okay. But I mean, in a second, you'll see that that's inconsistent with the data. Okay, so it's not going to be interesting for this case. Okay, but so there's this famous bound at cluster scales at like 1,000 kilometers per second, which comes, I mean, historically, the thing most people here would know is this thing called the bullet cluster. It's these 2 clusters that we happen to catch as they're moving through each other, like a small amount, it's like sub-giga year after they've hit each other. You measure where the gas is and you measure where the mass is through lensing, and you find that they're displaced from each other, and that sets a bound on the cross-section for self-interacting dark matter. It's actually old news. There's updated bounds that are a little bit stronger, but regardless, all of those bounds are about 1 centimeter squared per gram at cluster velocities, okay? So there's an upper bound of around 1 centimeter squared per gram at cluster velocities. So let's make a plot now of the parameters that I care about, okay? So I'm making a plot now of the underlying parameters of the model. So on the y-axis here, I'm going to plot omega in kilometers per second. On the x-axis, I'm going to plot sigma naught over m chi in units of centimeters squared per gram. And every point on the plot on the right here, right, like this bound is going to correspond to a line on this plot. And so that bullet cluster bound does something like this. It rules out a region like that of the parameter space where, this number is like 1,000, here there'll be 100, here there'll be like 10.
And this is given in n.
Sorry?
Given what this index is.
Given that you know n, exactly.
Yeah,
That's
for a
gonna,
particular-
that tells you how fast this thing falls off, exactly.
Okay.
Right, but this is for n equals 4. Good. Okay, now if you go to velocities that are a little bit smaller, velocities of the order of galaxies, then famously people who have worked on these models for many years, have made strong claims in the literature that the region between around 1 and 10 centimeters squared per gram does very well at explaining this thing called the diversity of rotation curves. Okay, so the claim has been as follows, that if you live approximately here, between like maybe 1 or 2 and 10, you're able to explain the shapes, the fact that the diversity claim is as follows, and I'm not going to go into this in detail today, is that if you look at halos, at rotation curves that live in similar halo masses, there's a very big diversity in the shape of the inner region of the rotation curves for those galaxies. And it turns out that self-interactions in this range explains that diversity very nicely, okay?
Or baryon physics.
Or baryon physics. I agree with you, but let me just say something about baryon physics in a second. I'll tell you why self-interactions do it, and then I'll tell you why the claims that were made were too strong, okay? So the reason that this works is as follows. It's because if you have an isothermal profile, when you have self-interactions, things thermalize typically pretty fast because heat flows efficiently. If you solve in hydrostatics, if you solve in equilibrium, what you find is that rho dark matter in the isothermal region is proportional to the exponent of phi dark matter plus phi baryon divided by velocity dispersion squared. Okay? So if you have an isothermal profile and you solve the hydrostatic equation, you find an exponential dependence between dark matter density and total potential, dark matter plus baryon, and this exponential dependence, which is coming just through gravity and the fact that you're requiring isothermality, goes in the direction of explaining this behavior, okay? Like some non-trivial correlation between the baryons in a galaxy and the rotation curve of that galaxy in the inner region. Now, in a paper that we published last year, we actually scrutinized this claim, and we found that, even though it's true, the statement, and you can fit lots of galaxies with like very few free parameters in this kind of model, people said that it was much better than CDM plus feedback, than cold dark matter plus baryonic feedback. But the statistics that people were using to make those claims wasn't great. Like, for example, claims were made about a model being a good fit when chi-squared per degree of freedom was much less than 1. And that should not be thought of as a good fit, that should be thought of as an overfit. So things like that were just like the statistic that was being done wasn't that great. And what we found basically is that you can do just as well with the data set at hand if you have 0 cross-section and baryonic feedback. So essentially, this boils down to there being some upper limit here as well. Okay, so you can have very small cross-sections, but baryonic feedback be important, and this turns out to be consistent. And this hasn't been quantified yet, but like qualitatively, this is just true.
But is that upper limit true, or is it just like there's no actual limit?
You mean there are two regions?
I mean that there's two regions that are just as consistent. That's what I mean.
Right, but the baryonic physics is like, it's a prediction.
Oh, you're right. But
Right,
in this
like-
region, you don't turn baryonic physics off. It's just that the time scale for relaxation SIDM is much faster than the time scale for the baryonic physics to be important. And so even if you have baryonic physics on, this SIDM model has this nice, this property that it doesn't care too much about feedback. It can core you or not core you, and the time scale for that is much faster than energy injection from supernova.
But for some reason, the baryonic physics that explains the rotation curve doesn't work at 1, but it works at 0.1 sigma?
No, well, at 0.1 sigma, the SIDM does nothing.
Right.
So there you only have baryonic feedback, and that's your only thing that can create cores. Whereas here, SIDM is strong and it can do things, but it's agnostic to what the feedback is.
Yeah, but why can you rule out 1?
Because
You ruled
baryonic
out
physics is parameterized too, I would guess.
No, but I guess I don't understand the question. What do you mean rule?
Well, you've look at
why is
at
that?
sigma equal 1, you've ruled it out.
Yeah.
Why is it ruled out?
Okay, well, I haven't ruled it out because, as I said, this has not been quantified. No one has done this analysis carefully. These things might overlap. It might be that there's just an upper bound here and everything else is consistent. I don't really know that this is ruled out.
Okay.
Okay?
All right.
It might be, but no one's done this analysis carefully.
But sorry, am I right or not that the baryonic physics is just indeterminate too, right? And that's why you tune the baryonic physics differently in that region.
I mean, again, like this is not, I'm not saying anything quantitative because no one has done this analysis. What I'm saying is as follows. You know, people made kind of non-statistical claims here, like no one has said, you know, this is the upper bound, this is the lower bound. People have like taken a constant cross-section of 3 centimeters squared per gram and checked, you know, does this fit data? And they found, oh, it fits data and it, you know,
But
does.
how can you say if anything fits the data, given that baryonic physics is really unknown?
Under the models that people write down assume that the baryonic physics in this region, when the cross-sections are large, are negligible. And they assume that because they calculate the time scale.
Which is totally arbitrary, right? Here you just switch off the baryonic physics, there you switch it on, and in both cases you are happy.
It's not arbitrary because if you calculate the time scale for relaxation with cross-sections of order 5, that time scale is much less than the time scale for supernova injection to do anything.
But ultimately supernova injection will do something, no?
Sure, but like you're coring from SIDM or whatever behavior SIDM, like the equilibrium SIDM solution happens regardless because the time scale for that is shorter. You don't like that answer. Why not?
That's okay, whatever.
Again,
Baryon physics is God knows what it is, right?
Again, I'm not talking, so this is not my work. My work has been to ask, you know, is the claim that people have made in this region, you know, is it statistically strong? And what we found, the answer is no. It's not statistically strong. It's equivalent to baryonic physics with, you know, in cold dark matter. So you cannot say, you know, one model is better than the other. They're both exactly, you know, statistically the same significance. Okay? And my interpretation of that is that really, you know, you can go down to low cross sections and you're fine. And it might be that these two things overlap, but yeah, that's all I really want to say. Okay. And let me just tell you what the underlying reason for this is, like why this is like obvious that this is what you expect. If you ask the question, you know, let's say you ask the question, how do these two models create cores or cusps? If you ask, you know, what is M star over M dark matter? Okay, I take a halo, I measure its stellar mass, and I measure its dark matter mass, and I take this ratio and I run a bunch of simulations. And if I do a simulation that has baryonic feedback in it, what I find is that at very low values of this ratio, feedback doesn't do very much, and you get cuspy profiles. And then at some specific ratio, you get cores because supernova is able to inject enough energy and core your profiles. And because of the way things scale at large ratios, feedback again is inefficient. Okay, so this is just a fact that you see in simulations. There's some magic number that does the best. Whereas self-interactions, they do well at these ratios. If you go down, they're able to core up to arbitrarily small values of the stellar mass, right? Because SIDM is able to create cores regardless of what the stellar mass is. And so if you want to differentiate between these models, you really have to go down to low values of this ratio, and all the data that has been used to make these claims is data kind of in the region that these two models are, you know, degenerate. Okay?
Right. Maybe it's kind of related to what we asked. I'm still confused. Why the upper bound on the self-interaction stronger in the lower cases? It's including baryon feedback. It's not about the gap between the two, but why it all? Like you're setting some lower bound there, assuming there are no self.
Sorry, this is an upper bound.
Sorry, the upper bound. Right?
Yeah.
And why this is upper bound?
Why is it contradicting the lower bound?
Yeah, no, I'm not asking about
Would
lower
everyone be
bound.
happy if I just did that?
Yes, yeah, that would be. Yeah, exactly. Right.
Okay. So then let's just do that, okay? This has not been quantified yet. I don't know the answer to this question. people previously claimed that like above 1 does better than below 1. We found that that's not true, but this is probably true.
And or why is the upper bound true? I mean, too isothermal doesn't make any sense.
Yeah, if you go to too large, I'll show you in a minute what starts to happen. The dynamics starts to be important, you start to core collapse, and you don't actually, this idea of being in equilibrium is no longer true. Okay, but again, no one has quantified that either. It might not be 10, it might be 20. Okay. Good. Okay.
It's related to last week's talk, right? Because you form a black hole. Like there's no definition of equilibrium.
Well, sure. I mean, it's slightly different because you had a closed system, and this is not a closed system, but it's similar. Yeah, and I'll show you exactly what the dynamics is in a minute. Good. Okay. So this is the picture. And the take-home message is, if you want to differentiate between these models, you have to go down to low stellar masses. Otherwise, you're degenerate, and there's nothing, you're not going to manage to make any big statistical claims. What I'm going to show you in a minute is that, so just to be clear again, right? So blue is feedback, and CDM, and red is SIDM. What I'm going to show you in a minute is that actually SIDM does this at moderate cross sections, but to answer your question, at very large cross sections, SIDM actually has a branch that looks like that. I'm going to explain to you this branch in a second. Okay? But regardless, you have to be here, otherwise the models are degenerate, and you have no chance of doing anything like significant. Okay. So now let's go down to these lower masses, and what we found in a paper that we published last year is that there is a lower bound of around 20 and an upper bound of around 1 at dwarf velocities. Okay? So in this language, what we found is that there is a region of parameter space between around 1 and 20 that is ruled out. Okay? And I'm going to explain to you how we found this, like in the next 10 minutes. Something, yeah?
Question did that because I thought Martin's question was about the upper bound, where it's coming from. Why is what you know answered this question?
Sorry, how does this? Oh, well, because if you go to very large cross sections, this becomes the picture and not this.
But that's becomes exactly this is the other one. So why that's the upper bound?
It's not exactly the other one, but well, okay. So at very large cross sections, it's going to look like this. Like that's the answer, and that is inconsistent data.
I'm confused about how your blue upper bound is this diagonal line on your left plot, but somehow your green ones are vertical.
Well, the green ones just start to curve. They're not vertical. Okay. I mean, they do that, but at a smaller velocity. Yeah. So this is this is what happens as soon as the Rutherford scattering starts to kick in. Good. Okay. So let me tell you how this bound was set. And to do that, I'm going to have to tell you about dynamics. Okay. Good. SIDM dynamics. So if you give me a sphere of self-interacting dark matter that is gravitationally bound to itself, and you let it go, you ask what happens as a function of time, that's what I'm going to try and answer on this board now. Okay, and everything I'm going to say is going to be true as long as m phi to the -1 is much less than n, the number density of the particles, to the -1/3. So I'm strictly going to be in the regime of short-range forces. And in the regime of long-range forces, this has not been studied. Okay? But I'm going to tell you the answer in the regime of short-range forces. And the answer is known because people have run simulations and because there's a fluid description. Okay, so basically, we're looking at a sphere of self-interacting dark matter, and we're letting it go and asking what happens. And I'm going to make 3 plots. I'm going to plot rho of R. I'm going to plot temperature as a function of R. And I'm going to plot core density, rho C, the density at the central region, choose some radius that you call central, and plot the density of that central region as a function of time. Good. Okay, and I want to start off with...
Sorry, is it kind of, should we think that in these dwarfs, baryons don't matter? Is it a good assumption?
It's a good assumption. These dwarfs are like 10 to the 8 solar mass in dark matter, at least, and like 1,000 stars. We're talking about, so like orders of magnitude.
So those are good pure systems
Those
for
are
you
good
to
pure
play with.
systems.
So
Those are
there are
systems
systems
that-
like LEOT, which has a huge amount of gas, and it's presumably gas that matters for you. Oh, maybe not. No, you're just worried about the potential.
Yeah, I mean, exactly. The potential, I think you're asking about feedback, yeah?
Yeah.
Just be sure I understood. This is going to be, so your inequality is that your something or other is either applicable or not applicable when the Compton wavelength of the mediator is small or big relative to the interparticle spacing.
Yeah, when the Yukawa cutoff is much less than interparticle spacing.
But anyway, what you're going to apply to that domain or the opposite domain?
I'm only going to be working in this domain.
Okay.
We're collective, there's no collective forces. Every particle at any given moment can only see one other particle.
Or 0.
Or 0. Right. Okay.
Sorry, could you explain again? I mean, we know that, like, because you mentioned like feedback is not important for dwarf collectives. But we know that in high redshift they are really wild. Like the feedback is really very important in dwarfs, right? Because they have like a strong feedback. They eject all the materials out.
So is this true for like an object like Draco, the Milky Way? Is that a true statement?
I'm talking just dwarfs. Like my expertise in high redshift, so the feedback is really important in these because they don't really form a disk, right? They are not in equilibrium state.
I mean, I think what you care about is whether feedback is important from the time, like the halo gets built up over time, and eventually it gets built up, eventually there's some time where the self-interactions become large enough for you to start caring about them. Like where the time scale for self-interactions is of order the age, the time left for the object to evolve. So do you know, I just don't know the answer to the question.
Okay.
If that holds, if from that time onwards, feedback is unimportant, then everything I'm going to say is true. If that doesn't hold, then maybe there's a caveat.
He's talking mostly in the ultra faint category, maybe fainter than Draco.
Well, I'm going to be talking about Draco and things like Segway 1. So Draco is going to be the brightest thing I'm going to be.
So they're just like, there's not a, just look at the total number of stars, a very small, I'm not saying he's right. I'm saying what he's arguing is that because the total number of stars is very small relative to the total available gas there would have been, then ergo feedback couldn't have mattered very much.
Yeah, and I think this becomes more true for things like Segway 1, right? That has like 100 stars.
I guess.
Yeah.
I mean, lots of other things happen, like all the gas is gone. All the ones that are known are sitting in the Milky Way halo. You'd rather have one out in the isolated universe, but those are very hard to find.
Things like the LEOT and so on are quite far
Yeah,
out of
and they're more gas rich for that reason. But
But I say I'm not sure with all the discussion I've focused in. You're going to look at, just say again what the logic is going to be, that you're looking at systems which did not have feedback, or
I'm going to be looking at systems that are small, where feedback is not so important, but that assumption of feedback not being important is not going to be critical because it would just make the bound stronger, I believe. So I don't think
the present conditions that matter or integrated over time?
Yeah, so for this, so there's different things. I'm going to be talking now about how to place this bound, This bound, really all you care about is that the time scale for coring is fast. And then all you care about is how you see it now, and if the time scale for coring is fast, you don't really care about that evolution too much. And then after that, I'm going to talk about what happens here. And here the evolution is important, and I'm going to kind of discuss how I think you can go after this region of the parameter space. So for this, it's not going to be too important. For this, it is. Like the orbit's going to be important, the history of the object is going to be important.
So one question, you said like in the case of very long-range mediators, it hasn't been done, but there's been people that have done this, right? Like there's this, like Robert Lazenby, did look at long-range self-interacting dark matter and type of plasma instabilities that happen in that case.
Right, but I don't think anyone's looked at like what happens to an object, like a dwarf that is, with this kind of model, right? Like a certain region of the dwarf feels a region around it collectively, but then a region, another, like it's not like gravity, right? It's different. I don't think the Lazenby thing can be directly converted into this language. You're right, I mean, people have looked at long-range forces. Yeah. Okay.
I just want to make one observation, one astrophysical comment, which is that the feedback in the dwarfs is important for the gas, but what you need is for it to not be important for the dark matter.
Right.
That's
you're saying
really
it removes a significant fraction of gas, but it doesn't inject so much energy.
Well, I don't know about what it injects, but the result that the feedback is important in these dwarf galaxies, mainly about the gas. It's not about the dark matter.
So I mean, this plot, this blue, is taken from like simulations. So I think it's known that when these fractions are small, typically you don't create cores. Yeah. Okay. So again, let's just go back to where I was. I'm going to now ask what the evolution of some profile is as a function of time. And to do that, I'm going to plot rho as a function of r, t as a function of r, and the core density as a function of t. And so if you start off with a profile that looks like this, a profile with, let's say, an NFW profile, with an r to the -1 at the center, and you solve for the temperature as a function of radius, you find something that looks like this if everything is in equilibrium. Okay, so cold, hottest, cold. Okay, and so what happens if self-interactions are efficient is that initially, if you ask how does heat flow in the central region of this object, it flows inwards. So heat can flow from like the scale radius of the object into the central region of the core. And so what happens is that you start off with some high central density, and as that happens, potential energy is converted into kinetic energy, and the core puffs up, and it becomes core, right? So this transitions into something that looks more like this. You wait long enough. Okay, so initially, as I said, you start off with like a region like this, so blue corresponds to blue, but then you get to some kind of long-lived state that is much more cored, and has a profile that looks like that. And if you plotted the temperature as a function of radius, you find that you get an isothermal profile at the center. Okay, so this is the picture that we all know and love about self-interactions. And this is what people studied for many years. This is the diversity problem solved. You wait a short amount of time, you thermalize the central region because heat flows inwards, you get an isothermal core, constant temperature, and any cuspy profile becomes a core profile. And this actually turns out to be an attractor solution, so it doesn't matter what you start with, you get this profile. But what happens now if you wait long enough is that you have a profile that looks like this. And so heat can actually now start flowing out of the central region, go in this direction. And what happens now is something called gravithermal core collapse. Okay, and this is a behavior that looks like an exponential increase in the central density. And the reason this happens, just let's plot it here as well. So what happens is you transition from this to this and then to this, and you get a very sharp inner profile that looks something like that, like an r to the minus 2.5 or something like that. And the reason that that happens is because if you write down the virial theorem for a gravitationally bound system, the object has negative specific heat, right? There is a relation between the energy and the kinetic energy that relates via a minus sign. So in these systems, if you remove energy from the system, that system actually heats up. Okay, what happens is that you remove energy and potential energy is converted into kinetic energy by the object shrinking and increasing in temperature and density. And because it increases in temperature, heat flows out more efficiently, right? Essentially what happens is that you get, hotter and hotter and hotter. And as you get hotter and hotter, heat flows out more efficiently, and it's a runaway process because of this minus sign. Okay? And that corresponds to this phase known as gravithermal core collapse. Good. Any questions about this? No. Okay. So basically, this is the picture that was used to set the green bound over there, because if you go and you measure the central density of objects in the Milky Way, many of them have central densities that are pretty large. So if you, for example, measure the central density of this object called Draco, you find that it has a central density somewhere around here. And if you write a code that takes into account all of this physics and also the orbit of the object and everything else, you find that the orbit of the object doesn't matter too much, and that the other unknowns you can marginalize over them. And what you find is that no matter how you play this game, you can never live here, because in this region of the parameter space, Draco overcores. So just to explain what I mean, an example is, we don't know what the total mass of Draco is. And so to set this down, in every position in the parameter space, I just choose the mass of Draco to give the weakest possible bound. And what you find is that between around 1 and 20, Draco is ruled out by more than 2 sigma. Okay? So what's happening here? Here, you're living in tiny cross sections, right? You might as well just call this CDM. And heat flow is inefficient and nothing really happens. Then you grow in cross section and you're in this regime. You're in the regime where coring is efficient, but you haven't had enough time to gravithermally core collapse. And so you core objects like Draco, and you core them too much, no matter what you do with their mass and their concentrations. Then as you go to larger cross sections, this time scale for core collapse becomes of order the age of the object, and then you're able to collapse and you're able to reproduce the central density of Draco again. Okay, so is that clear? Okay, so the take-home message is, if you believe in the story, there's 2 consistent options. Option 1 is the CDM option, the tiny cross-section option, and then you just, you can call it SIDM, but you don't have to, just call it collisionless dark matter. Or you live in this region of the parameter space where gravithermal core collapse has to be happening, or has to have happened for some of the objects of the Milky Way. It has to have happened for Draco, Ursa Minor, Segway 1, and Tucana 2. These are the 4 objects we looked at, and like now we're doing a full Bayesian analysis of all the objects of the Milky Way. But basically, in this region of the parameter space, some objects in the Milky Way have to have core collapsed, otherwise you're inconsistent with data.
There's no black hole forming?
You can have a black hole form, it depends on the cutoff of the theory, but that doesn't really matter, right? What you get is a power law in your density up to like some tiny radius, and then maybe a black hole at the center that doesn't really do very much.
This sounds funny, right? Because large cross section means you become a fluid. And
okay, I'm about to talk about this.
Oh, you will.
I'm about to talk about this. Okay, it turns out that even at small cross sections, you can think of it as a fluid, even though it's not technically a fluid.
I'm just saying the equilibrium might exist, but the formation scenario perhaps does not, because fluids don't form this self-gravitating halo.
Okay, good. So you're right, and actually, like the truth is, there's another bound here that no one has placed yet. Okay, where what you said now is true. So that's actually an important point, because if you go to super large cross sections, you again are going to be ruled out, but no one has done this work yet. But just to say, there's a kind of small region of the parameter space that remains allowed. But you're 100% right. Okay? So when the mean free path becomes like much less than the size of the object at very early times, what you said is correct. Good.
Sorry, maybe related to this, in the opposite limit, usually in a weakly coupled, let's say gas or fluid, transport coefficients are proportional to the mean free path.
Yeah, I'm going to talk about that right now.
Okay.
That's the next part of my talk.
Because you said that heat transfer is very inefficient at small cross sections. Isn't that the opposite? Usually it diffuses so easily that heat conductivity is very large.
Think about this. I mean, typically the story with heat conductivity is that it goes like the mean free path times the velocity, right?
The velocity dispersion, something like that.
Heat conduction becomes large, but it does not do the same thing.
Exactly. Yeah. Right?
You cannot even call it heat anymore. It becomes
like it's difficult to even define a temperature in that limit,
exactly.
right? Yeah.
So it doesn't thermalize.
It doesn't thermalize for sure. Yeah. Okay. But let me just talk about exactly this topic now. So the next part of the talk, I want to talk about the fluid description of the story, right? Because basically where I'm going to go with this now is, how does one probe this region of the parameter space? So something very violent is happening here. Gravithermal collapse is happening in Draco. It's happening in a lot of objects in the Milky Way. This must be something that that we could search for, okay? And what I'm going to tell you now is that I think it is, and I think the way to move forward is to understand a fluid description and scan over parameters carefully, okay? And so that's what I'm going to tell you about now. And so the topic now is going to be SIDM dynamics and the fluid description, okay? Or kinetic theory. Good. So the question is there a fluid description? The answer is yes, even though formally you wouldn't have expected it. And I'm going to tell you why that is now. And so really the question is, can we write down a set of macroscopic fluid, parameters or fluid-like fields, like density, temperature, pressure, heat transfer, heat conduction, and velocity and bulk velocity. Can we write down a set of properties and then write down a set of closed equations, some 5 equations that govern these things? The answer is going to be yes. And one way to think about this is in the language of kinetic theory. And in the language of kinetic theory, what you do is you write down the Boltzmann equation. Which is just df dt equals 0, okay? So f is the one particle distribution function. It's a PDF that answers the question, at position x and velocity v and time t, what is the probability of catching a single particle? And it's a good description of systems that have identical particles. And you can write this down in partial derivatives as df dt plus v df dx minus d phi, the potential dx df dv. And this thing needs to be equal, maybe not to 0, but to a collision operator. And when you the way you get a fluid description is by writing down moments of this equation and asking, do the moments truncate at a finite level, right? Can you write down a finite amount of moments that govern a finite amount of these things and have a closed set of equations? And to do this, you need to define things like the number density. So the number density is just the integral of f d3v, and the velocity is equal to 1 over n times the integral of f times v times d3v, and you can continue writing down these things, and then you can take the Boltzmann equation and multiply by things and integrate over d3v, and you get a set of equations. So for example, if you integrate 1 times df dt d3v, what you get is the continuity equation. Okay? And if you do the same thing but multiply by v df dt d3v, you get the hydrostatic equation.
Sorry, in this corner of parameter space, what's the ratio of the mean free path to the size of the system?
Large. Okay?
Then this is just a waste of time.
Yeah, you would think, but it turns out not to be. And I'll show you why in a second. Okay? Okay, and then, so this is equation 1, this is equation 2. Equation 3 is the energy equation. Energy. There's another equation, which is the equation of state. So you can assume like an ideal gas. Okay, so that gives us 3 equations. And the 4th equation is the equation that you would have complained about naively, which is the following.
Wisely.
Sorry, what?
Not naively, wisely.
Wisely. Sorry. And that equation is the equation that relates Q to the gradient of the temperature. Okay? And this is a good thing to write down only in the limit where the mean free path is much less than changes in the temperature. Okay? In kinetic theory, just to kind of say this formally, what you do is you write down an F which is equal to F Maxwell-Boltzmann plus some small correction to that Maxwell-Boltzmann, and this small correction, delta F, you can write it down as being F Maxwell-Boltzmann times some arbitrary function g times grad t divided by t. And when this thing is much less than 1, then it turns out that you can write down a nice equation like this. But this g is typically of order the mean free path. And so you have to have the mean free path, you know, be much less than gradient of t over t. And when that's not true, you typically cannot write down a nice kappa like this. Okay, that's what was bothering you, right? Is that true?
Yeah,
Yes.
of course.
Good. Okay. So what's the story in this particular scenario? So here is my dark matter halo. And what's really happening is that I have orbits, right? I have a particle orbiting, and then once in a while it collides. And after it collides, it changes its orbit and does that. And then it collides again. Right? And then it does something like that. So the question is, what is the typical distance between collisions? And the typical distance between collisions is of order the size of the object. So even though the mean free path is very large, because these things are interacting in the core typically, the real distance you care about is of order the size of the core. And so what happens is that you have some core size h, and the velocity that you should be thinking about, the time it takes, you know, is the size h divided by the time it takes the particle to, you know, do all of this and then collide again. And that time is just the time scale for collisions, okay? And so what it turns out is that because this is true and this h is of order delta t over t, you can write down a nice kappa, and that kappa goes like h squared divided by t collision, where t collision is just the time scale for collision, which is, you know, approximately equal to 1 over sigma n velocity dispersion.
Whenever you have a closed system of some sort, you're always going to satisfy this condition, right? Like, because things have to happen inside the system.
That might be true, but like, yeah, this is similar to what happens when you have like a capillary system, right? Where like you're hitting the walls. This is related to Knudsen theory, and like what happens.
Yeah, I don't know what that is, but
yeah, but I mean, you're asking, does this happen in other systems? I think the answer is yes, sometimes.
okay.
Yeah, and look, what I'm saying here is kind of hand wavy. I agree, but this is the same. Like people write down these equations for globular clusters, and they're using the same type of logic. And so this is kind of me interpreting why this is true.
Qualitatively, it should be okay.
Qualitatively, and it might be that you need another expansion to get this exactly right, but like qualitatively, it turns out to work. So if you write down these things and you solve these equations, you get very close behavior to what you see in simulations.
Did any? Oh, so people did simulate.
Yeah.
Like in molecular dynamics or whatever.
No, that you
like with collisions, with actual collisions.
Yes, with actual collisions. Yes. And what you find this behavior, and these equations, if you solve them for these variables, you find the exact same thing, up to like order 1 corrections. Good? Okay, so this is me just interpreting that. Okay, but you can understand where the intuition is coming from. Good? Okay, so in the last 5 minutes, let me talk about signals. And so the strength of this is that now if you have this description, you can write down a set of equations, you can scan over parameters, you don't need to do, you don't need to run simulations, it's very computationally easy. And you can attempt to now ask, what do you expect in this region of the parameter space? And maybe try and set some new bounds or, look for signals. So in the last part of the talk, I'm going to talk about astrophysical signals. And really what I want to talk about is that everything I've said so far has been kind of idealized. If you have a real system, it's not just, living in a vacuum and doing this dynamics, but really you have a satellite that's orbiting a host and it's experiencing things like tidal stripping and all sorts of other things, right? And so in order to really get a kind of sense of what's more realistic, you need to think about those, these are not systems, environmental effects are important. Okay, and so I want to talk about 2 important environmental effects, and I'm going to end with that. And so, imagine you have your dwarf galaxy, and it's orbiting the host, and there are some particles that live inside, and they're colliding with each other, like this, and they're causing this entire dynamics that we talked about. There are also particles that belong to the host, and there are also self-interacting dark matter particles. And so I want to talk about 2 effects that are important. One effect is just gravitational, right? This object gets tidally stripped as it moves through the background of the host. So tidal stripping is one important effect. And then the second effect that is important is that there are self-interacting dark matter collisions between the red particles and the blue particles. And those collisions are happening at velocities much larger than the escape velocity of this object. And so almost every collision results in evaporation. It just removes the blue particle. Okay, so as this guy moves through, there's ram pressure, but not in the gas sense. It's ram pressure in the particle sense. It's happening with a long mean free path, so it actually does not go like v squared. It goes with a power that depends on the cross section. And these particles are basically able to penetrate through this entire object, get to the center, and remove mass efficiently from everywhere. And so the second effect is ram pressure evaporation. Okay, so it's very easy to incorporate these 2 things in the fluid description I talked about here, right? Tidal stripping, all you need to do in order to incorporate it is at any given moment in your numerical code, you just need to truncate your object at some radius and ask what happens, and you can get intuition as to what the effects of tidal stripping are, right? So you take your code, and then at some moment in the code, you have your profile, your dark matter profile, which is evolving, whatever, and then at some moment you can truncate it like that. That's approximately what tidal stripping does. And what that does is it changes the gradient of the pressure on the outskirts, and the effect is as follows. So rho c is a function of time. For the vanilla case, we said it does that. If you incorporate tidal stripping, what happens is the time scale for collapse decreases because the outskirts become colder, so heat flows out more efficiently, so the time scale, so core collapse can happen over a shorter time scale. Okay, and actually this effect was included when I placed this bound. Okay, so in this region, core collapse can happen, including this effect of tidal stripping. What has not been studied is the effect of ram pressure evaporation. And ram pressure evaporation is very easy to incorporate, all you need to do is you need to go to your continuity equation and add a term that goes like minus gamma evaporation times rho. You just need to add this term to the continuity equation and solve. When we've done that, what you find is that core collapse starts to turn off as gamma EV increases. As you increase the evaporation rate, core collapse turns off, and if you increase it too much, core collapse completely turns off. Okay? Now this is important because, as I said, data of the Milky Way needs core collapse. So if anything turns core collapse off, that's ruled out. And so we've solved this, right? What you get is you get a picture that looks like this. The density as a function of radius. Let's say you start off with a profile like that, and then you get a profile that looks like that, and then slowly the profile just starts.
I'm sorry. You said data needs core collapse, but the actual dark matter is not interacting, and so this core collapse apparently happens in a different way or something?
No, this is self-interacting dark matter.
Yeah, you are talking, but I live in the real universe.
No. You can also be here, that's fine.
Ah, okay.
I'm just talking about this region.
Okay, in this region you do need enough core collapse.
Yeah. For cross sections that you would call self-interacting cross sections, you need core collapse.
Okay.
That's it.
Clear. Because I thought you have claimed discovery of self-interaction.
Not yet.
Okay.
Okay, and so if you do the math, okay, so I'm going to end with this because I think this is the end of the talk. But just to kind of give you a nice little picture of where you can go with this. Let me just use this. So basically, this curve, for example, is a curve that must be ruled out. Because if core collapse cannot happen, if evaporation rate is large, you're inconsistent with data.
Specifically, just even the existence of the dwarf galaxy, is that right? Am I still on the right wavelength?
What do you mean?
I mean, what aspect specifically is it?
The central density of Draco is too large to
As
not
measured
have
by like the velocity dispersion of the stars?
of the stars. Sure. Yeah. A measurement. You take velocity dispersion of stars. You marginalize over the fact that you only have 2D velocity dispersions. Whatever. What you find is you have some density, some average density enclosed within some radius. That value is inconsistent. Yeah. If you want to explain it with large cross sections, core collapse has to have happened. And so, I don't really have time to go into the details, but basically what you want is you want core collapse to be on because you want these internal collisions to be fast. You want these external collisions to be slow because they evaporate, and that's, I'm going to say the word bad, that's bad for SIDM. These internal collisions are good for SIDM. And so what that corresponds to is it corresponds to having a small omega because you want this power law to help you. You want large cross sections for low velocities and small cross sections for high velocities. And so if you do like a back of the envelope, it corresponds to like ruling out a region like that, approximately. Okay, and that is a bound we're going to place soon, hopefully. And you can imagine that even in this region, there's a signal, right? You expect like some anti-correlation between the evaporation rate and the central density. And maybe I'll end with that, but like just to make it clear, in this region of the parameter space, there's signals that you can imagine searching for. And let me talk about that with anyone who's interested another time.
Thank you. So we had lots of questions. So I think we're just going to break it here, but of course Oren will be available right now.
Yep.
For the foreseeable future. Thank you.
Is there a cookie and coffee?
There should be, yes.
Well, if anyone Everyone sees a little blue fanny pack. I must have dropped mine
This
somewhere.
envelope of coca
No,
leaves.
in 2 days, I'm back at the
It's not, no, there's a completely different story. There's a hierarchical structure formation and creating NFW
I mean,
profiles.
we'll find it out.
No,
Yeah, next week.
no coconut.
Yeah.
You have an R to the -1.
But in actual observations, because your things you also start with
Shall I
NFW.
end the recording or?